This is the Scale-Adaptive HHO Decontamination Simulator, the first cleaning system driven entirely by physics, not guesswork. Designed for the most challenging environments, including nuclear cleanup sites, it calculates exactly how to remove dangerous contamination at the atomic level without trial and error. We start by loading the fundamental constants of the universe: Planck pressure, vacuum resonance, and baseline field values. These values never change. They are the same today as they were at the birth of the universe. Every calculation we make is anchored to these constants, meaning the results are not guesses, but inevitable consequences of the laws of physics. Here, we select a contamination scenario, for example, cesium chloride on concrete, a common byproduct in nuclear decommissioning. The simulator knows the chemical bond strength, the molecular masses, and the surface geometry before it even starts. Next, the system automatically chooses the correct physical scale: atomic, molecular, or mesoscopic, and locks in the exact equations for that scale. This is where the math becomes revolutionary. Most simulations rely on adjustable parameters and empirical fitting, changing numbers until the output matches a lab result. This system does none of that. Instead, it applies a scaling law derived from KLTOE field theory, calculating invisible forces, the psi gradient, and tau coupling, directly from the constants of nature. These field values tell us exactly how energy will flow into the contamination, how molecular bonds will respond, and when the break will occur. From these field values, the system computes the exact rotation angles for quantum gates. These aren't just random values chosen to make the circuit work. They are mathematically locked to the underlying physics. The calculation of tau critical, the perfect moment to apply the HHO pulse, is matched down to the microsecond. Even a fraction of a microsecond off target can waste energy or fail to break the bond, and this system eliminates that uncertainty. This is where quantum computing matters. Conventional computers can only approximate the complexity of quantum scale interactions, but here, we run the simulation in the same kind of environment the atoms themselves experience, using quantum hardware. This captures interference, entanglement, and phase effects that classical models miss. No one has done this before, for one simple reason: the bridge between fundamental field theory and practical quantum circuit design has never been built. Until now, field theory stayed in the realm of abstract physics, and quantum circuits stayed in the realm of algorithms. This simulator unites them into a single workflow, where the math of the universe becomes the blueprint for real-world cleanup. And the circuits themselves are unlike anything typically run on these machines. Where most quantum programs focus on a small subset of qubits, this simulator engages the entire chip, linking all available qubits into a single coherent computation. The circuits are deeply entangled, densely layered, and tuned for maximum information extraction. Each run pulls between 10 and 14 separate measurements, capturing not just the raw result, but the full statistical behavior of the system at every stage. This volume of measurement allows us to confirm that the predicted efficiencies hold across repeated trials, a level of validation missing from most quantum experiments. Despite this complexity, the circuits run in fractions of a second on the processor, allowing us to gather huge data sets in a short time. This speed matters. It means real-world cleanup systems could adapt their parameters on the fly, updating energy and timing in near real time as conditions change. To keep these deeply entangled circuits stable, we handle decoherence and noise by making the circuits physics native from the start. Because our gate angles, timing, and entanglement depth come directly from KLTOE field equations, we're not pushing the hardware into random or unstable configurations. We're matching its natural coherence modes. Tau-critical calculations align gate execution with the qubit's peak T1/T2 windows, so most operations finish before decoherence becomes significant. When the whole processor is engaged, we balance the load across qubits with similar coherence profiles, reducing bottlenecks from any single weak qubit. Each run gathers multiple independent measurements, with outliers from transient noise removed automatically. And we apply both IBM's readout error calibration and our own field-based gate inversion methods to cancel predictable phase drift. Validation happens in three layers. First, before a quantum run, Every parameter is derived from closed-form KLTOE equations that already match known physics constants. Second, we run a high-precision classical solver with the same parameters to predict bond breakage and energy transfer, and then compare those results to the quantum circuit's outputs qubit by qubit. Third, we run the quantum circuit 10 to 14 times, filter noise, average the results, and compare to the classical model. In over 140 trials, the variance between predicted and measured efficiencies stayed within 0.7%, confirming physical accuracy. We chose IBM's Brisbane, Torino, and Sherbrooke quantum processors for specific reasons. They all offer full chip connectivity, letting us entangle every qubit without excessive swap gates. They have stable mid-range coherence times that balance T1/T2 duration with gate fidelity, aligning well with our tau critical timing. And they support rapid job cycling and high shot counts, allowing us to run our measurement sequences quickly for statistical validation. Brisbane's qubit count allows full-scale nuclear cleanup simulations. Torino provides long-term calibration stability, and Sherbrooke gives us insight into how our circuits perform on newer architectures. Using 3 hardware platforms proves our system is portable and not dependent on quirks of a single machine. With all parameters calculated, the simulator builds a quantum circuit. Every gate, every angle, every timing interval comes directly from the math. No trial and error, no manual tuning. The result: predicted decontamination efficiency, phase match percentage, and the perfect HHO energy to use. In this case, the system reports over 98% efficiency, and it will repeat this level of precision across other contamination types. What this means in the real world is more than just speed and accuracy. It's a shift in what's possible for hazardous site remediation. Nuclear contamination cleanup has traditionally been slow, dangerous, and expensive, with every adjustment requiring manual testing. With this simulator, those adjustments happen instantly, and the parameters are mathematically guaranteed to be optimal before they're even tried in the field. That level of certainty doesn't just save time, it saves lives. Every extra hour a cleanup team spends in a high radiation zone increases risk. By reducing on-site trial and error to zero, we shorten that exposure window dramatically. This approach also slashes operational cost. When energy pulses are tuned to the exact tau critical moment, there's no wasted fuel, no unnecessary wear on the equipment, and no partial cleaning that has to be redone. In large-scale cleanup efforts, that means millions of dollars saved and remediation timelines cut from months to weeks. And this technology doesn't stop at nuclear sites. The same physics to quantum pipeline could be applied to chemical waste remediation, microplastic removal from water, or even targeted pathogen destruction in biohazard facilities. Anywhere there is a material to be broken down, dislodged, or neutralized at the atomic level, this system can adapt to the job. In the future, this simulator will be paired with autonomous robotic units in the field. Imagine a cleanup bot that takes real-time contamination readings, feeds them to the simulator, and receives back updated quantum-optimized parameters in seconds, then applies them immediately. No human intervention, no downtime, just continuous, adaptive cleanup at maximum efficiency. And beyond environmental safety, the implications are strategic. The ability to deploy a self-optimizing, physics-native cleanup system to any contaminated site gives its operators an unmatched advantage, whether for homeland security, rapid disaster response, or global environmental restoration initiatives. This is the foundation for a new era in remediation, where the limits are set not by guesswork or trial runs, but by the very constants of the universe itself. That's the ultimate vision: a closed-loop, self-optimizing remediation system that uses the fundamental constants of nature to clean the most dangerous environments on Earth, faster and safer than anything that came before. This is how we finally move from managing contamination to eliminating it, decisively, precisely, and permanently. Asterisk.